Hello everyone, I'm Lucas Alegre, and I'm going to present our work on minimum delay adaptation in non-stationary reinforcement learning via online high-confidence change point detection. We, as humans, besides having learned to walk in regular conditions, we also have the ability, for instance, to learn novel gait patterns to use when walking with crutches after suffering an accident. Similarly, we can also quickly adapt to walk in different complex terrains. This is possible because as humans are capable of learning to solve new tasks from few experiences, and we do so while preserving the knowledge from past contexts, which can introduce internal and external changes from our perspective. But can we design artificial intelligence agents able to adapt to non-stationary environments? That is, agents that can adapt their decision-making policies to different kinds of unexpected perturbations. The key challenges that we try to address in this work are how to quickly and reliably detect when the underlying system dynamics has changed, how to learn adaptable policies and prediction models, and how to reuse older knowledge, avoiding the problem of catastrophic forgetting. We introduce model-based reinforcement learning context detection. While standard reinforcement learning algorithms struggle to deal with non-stationary changes, our method allows the agent to quickly detect the current context and adapt its policy accordingly. Our contributions include MBCD, which uses high-confidence change point detection statistics in real time and has formal guarantees of minimizing the delay of detection and do so while bounding the false alarm rate. It incrementally builds a mixture model of probabilistic dynamics and policies specialized to different contexts, and we also show that MBCD outperforms state-of-the-art reinforcement learning algorithms in high-dimensional continuous non-stationary tests. Importantly, it assumes unknown boundaries between contexts, and that contexts can be drawn from arbitrarily different distributions, which is a strong assumption of meta-learning algorithms. We define non-stationary environments as a family of MDPs, where each MDP differs by the joint conditional distribution of the next state and reward given the current state in action. During its lifetime, the agent interacts with a random sequence of MDPs. The random time steps in which context changes occur are called change points. We assume that the prior probabilities of the change points are unknown to the agent. We can then perform online change point detection with high confidence using Kusum statistics. These statistics are computed using the log likelihood ratio between the probabilities given by the dynamics of two different MDPs. Intuitively, when the model of MDP 1 is more likely to have generated the transition than the model of the MDP M0, the log likelihood becomes positive, and the Kusum statistics is expected to increase. Then, a change is detected at the first time step in which the Kusum statistic reaches a given threshold. Kusum has the property of giving an approximation for the worst expected delay, which depends on the KL divergency between both models and in the bound for the false alarm. Now I'm going to present a brief overview of MBCD. Given the current state of the agent and the current context belief Z, the agent chooses an action with the corresponding policy among a set of previously learned policies. A mixture model of dynamics with probabilistic predictors for all known contexts predicts the probabilities of the next state and reward. Then, multivariate Kusum statistics are computed for each known context. The current context belief is then updated in case any of the Kusum statistics reaches the detection threshold. In case a new context is detected, a new dynamics model and a new policy are added to the mixture. Here, we show the total reward achieved by different algorithms as the context changes. Each colored shaded area represents a different context, including joint malfunctionings, wind, and changes in the target velocity. After having observed each context at least one time, MBCD successfully recognizes that previously learned policies may be redeployed and avoiding having to relearn each policy again. MBPO and SAC, however, continue to suffer from catastrophic forgetting. Next, we compare MBCD to meta-learning algorithms. In this experiment, each method had a pre-training phase with contexts where a random joint of the Haupt-Theta were disabled. Although we consider meta-learning methods have lower variance in their performance, their meta-learned models do not perform as well as the MBCD context-specific policies. In summary, We introduced a model-based RL algorithm that efficiently learns in non-stationary settings with high-dimensional continuous state spaces. We showed that high-confidence change point detection statistics can be combined with reinforcement learning to enable adaptation with minimum delay, outperforming state-of-the-art reinforcement learning algorithms. As a future direction, MBCD could be improved in a combination with policy transfer learning algorithms. A limitation of our method is dealing with environments that instead change slowly and gradually. We invite you all to check and read our paper and ask us questions. Thank you.